The reason that we're going to be doing a ton of clicking today is because we have the regular clicking for lecture, and then the last 20-30 minutes, hopefully we'll have a review session here in class using your iClickers in self-paced polling mode, kind of like what we do on exams, except you've got 21 questions, a one-page handout, which we'll get out to you in a few minutes. This big stack of stuff up here. So, but let's get back to gravitational lensing and black holes. Last time we talked about the light cone, and we also talked about escape velocities, and I want to mention a few escape velocities to you right now. So go ahead and add this to your notes. The escape velocity for a black hole is the speed of light or greater. I mean, we can, and even back in the 1700s, an English physicist, I believe his first name was John, last name Mitchell, he said, well, if Sir Isaac Newton's theory of gravity is true, the inverse R squared law, then you should be able to get an object that's so heavy that its escape velocity is greater than the speed of light. And so that's what we call a classical black hole. In Einstein's theory, the black hole is defined differently, but it's actually equivalent to escape velocity, the speed of light, or greater. Okay, for Earth, escape velocity for Earth, 11 kilometers per second. So these guys at Cape Kennedy, at the Kennedy Space Center, if they want to send something out to the outer solar system or up to the moon even, 11 kilometers per second or more is what they have to develop. So they have to have really big rocket engines, and they've got to get a lot of second stage, third stage action, a lot of burning. The sun's escape velocity. Sun is bigger. There's a bigger radius, but a lot more mass. The sun's escape velocity around the photosphere, 618 kilometers per second. Go ahead and make a note of that. Mars escape velocity. Any guesses for Mars? It's smaller. It's a planet. It's smaller than Earth. More than 11 or less than 11? It's less, and it's a lot easier, 5 kilometers per second. Now the moon is the easiest of the lot. And you can look up all the other planets, we know that on the moon, it's, the Apollo astronauts, you've seen the movies, hopefully, they go jumping around like better than Michael Jordan up there because gravity's so weak. And for that reason, another implication of that is escape velocity for the moon, 2.4 kilometers per second. So Earth is, the planets are in there, the sun is ginormous, and you can imagine other astrophysical objects for which the escape velocity is bigger and bigger. The sun is about, about 60 times greater, 55, 60 times greater than Earth's escape velocity. And so there's stuff, that's escape velocity is the speed of light, and that's good. Now, I have a clicker question for you, and I want you to answer to the best of your knowledge. Now, this is by way of a survey, so give me your best educated guess, all right, on this one. And I want you to think, is it possible to make a map of the entire infinite XY plane? So the x-axis and the y-axis, from infinity to infinity in the x direction, infinity to infinity in the y direction. Is it possible to make a map of that, the entire thing, on a finite piece of paper? Yes, no, or no way. So there's one yes and there's two no's. Go ahead and vote. Can you select those? That's strange, the touch screens. I was doing it all day on Tuesday.
Maybe you can turn it on and off.
Yeah, I don't know what the story is. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, actually deselect. No, don't worry. Go ahead and show this. All right, now here's what you guys voted for. The majority, 54%, voted NO. Minority, 46%, voted yes. Go back to the regular display, please. Okay. The answer is yes. I want you to write down the question, if you haven't already, and write down the answer. And this is actually related to some of the unusual things that happen with a black hole. And I'm going to show you the geometric structure of this mapping process. In other words, I'm going to show you a plane, like here's the plane. This infinite x and y, infinity left and right, infinity up and down. And I'm going to show you how to choose any point. Pick, like they say, pick a card, any card. Pick a point, any point on that plane, and I will show you how to map it easily onto a finite-sized piece of paper. The key is to make your paper a sphere. Here it is. If you take a sphere and you take a dot over here, point S, on the plane, so this is the one, pick a point, any point, and you draw a straight line from the north pole of the sphere all the way out to that point S, it's going to poke through, there's point S, here's the poke through point, right? So that is a point, in this diagram it's labeled point P. It's on the spherical piece of paper. You don't need infinite paper. And that's the only point that, these 2 points are unique. Point S will only go to that point P on the sphere. And that point P on the sphere, it doesn't match up to any other point. If you do this procedure of drawing, here's another one, a straight line from the North Pole, and this one has the sphere sitting on the plane, a slightly different projection. So if you take, here's another one, any point down here on the plane, and go from that into the North Pole, it's going to poke through, like right here, for this guy down over here to the left, or it's going to poke through right here for this guy down here in the bottom, in the middle, or maybe this one up here. You've got a point way out here. Now, this is a classical exercise in the math department in a geometry class, and so go ahead and make your notes. A sphere can map the entire infinite XY plane without breaking a sweat. And this is the mapping method. All right? Your poke through point is your map. All right? And the sphere, it's surface area, 4 pi r squared. So you need a finite amount of paper. Now, here's the thing about it. This point here in the lower left on the plane, that's fairly close to the sphere. And this one over here on the far right towards the middle, that's the furthest one out of the three that we've got on the plane. The closer you are to the further out you go, the closer the poke-through point here gets to the North Pole. So let me repeat that. You can jot it down in your notes. The further out that you go on the plane, the corresponding poke-through point is going to be closer and closer to the North Pole. So, now, what point maps out to the North Pole? Infinity. And so what you've got here, you don't just have the entire plane pick a point, any point. You've got infinity mapped directly onto the North Pole of this sphere. So it's kind of cool. It works really sweet. Now we're going to be thinking about, black holes, it's all geometry. That's what Einstein's insight was. Forget about gravitational forces. Think geometry. Think the curvature of space-time. And we got a little bit of thinking to do. So let's get back to black holes. All right, so that's your little exercise. And keep your clickers ready because we're going to be doing some more. Last time we discussed the idea of gravitational lensing. And gravitational lensing, not as like your eyeglasses, the lenses in your specs. That's a process called refraction. R-E-F-R-A-C-T-I-O-N. Like a prism. A prism refracts light. Your eyeglasses reflect light. Just the right size to focus it on your retina and stuff like that. If you use them. If you don't use them, anyways, that's how eyeglasses. But that's not what gravitational lensing is, because there's no glass out there in space. But what there is curvature. So we call it a curvature effect. Now, last time we talked about the deflection of starlight. Here's a diagram of it, and we said that if you observe, for instance, the stars that are near the sun during a solar eclipse, when all the glare of the sun is covered, is blocked by the moon, then you can sometimes see and measure the deflection of starlight. So this diagram, the key is this idea of actual position and apparent position. And there's three examples here. The closer you are to being behind the sun, the more the apparent shift outward. And so this medium one here in the middle, it's got a little bit of shift to a new apparent position. And we know from eons of observation that its actual position is here. It looks here when it's grazing by the sun. And then this third one down here, no, you're too far away to get a whole lot of curvature from the sun. The sun's got some curvature, but only for light rays that go really, really close. And this diagram is exaggerated. Now, here's another diagram that I stole from the internet. And you'll see, just put in gravitational lensing. You'll see buku images like this. And this one emphasizes that the gravity of a massive object like the sun or a black hole, it bends the fabric of space-time, and then the light follows the contours of the curvature of space-time. So it's like those little games that you see at the mall and stuff, where you take a coin and it's like this round funnel that it's not a cone. It kind of gracefully eases down into a tube, and you put your quarter in it, and it spins around, and it goes really fast. And as it gets closer to the center, it starts to go really, really, really fast, and then finally it drops in, and you make your donation to to whatever the society is. Okay, those little machines. Raise your hand if you've seen one of those things. Yeah, okay. Bunch of you. Right, so you see them in the walls and stuff like that. And so that's kind of an example where you see something like this every day. So this is like the quarter going past the hole, the curve, and when it's in the curved area, it deflects. Now notice out here the graph paper up here is it looks pretty rectangular. Well, it's on a slant, but it looks like regular conventional graph paper. But whoa, look at these graph paper lines down here near the star. Big trouble. All right, and that's where the deflection occurs. Here's another one. This one's nice. And the thing that you want to emphasize here, you might like this sketch. Deflection of starlight, we can actually measure it. Because of the deflection of starlight, the star appears to be out here. It's actually over here. And the starlight is deflected just right in here. So this is where it gets budged out of its normal straight line trajectory. All right? And so it's actually coming in along this line. All right? Now, normally, if there were no SUN there, that ray would buzz right past the Earth. But because the sun is there, down here, it changes its direction, and it appears to be coming from this direction. All right? So, true and apparent positions. All right? And so the general idea is here's another look at the general idea. This time you're looking at the sun. And you're going to get, and the little blue arrows measure the deflection of starlight. In other words, from the position to the apparent position of the star. So stuff out here, it's fairly close. That star is fairly close to the sun. It's going to have a starlight deflected a little bit in that particular direction. So the tip of that arrow is where you'll look for that star. Okay, you won't look for it in the original position where the little box is at the end of the arrow. Now, if you're a little further out here, the lensing is a little weaker. So you deflect a little bit. The trajectory of the photon, the starlight, from that star, it's bent a little bit, but it's not ginormous. All right, so that's kind of what we see. And the stars appear in kind of random positions and stuff, so that's reflected in this diagram. So, the stars that you can see deflected, and we can see this happening with the sun and other objects. The other thing is, if you have something that you should not be able to see, like a galaxy that's completely behind your central object, like the sun, if you have something that's behind there, gravitational lensing will push it out, deflect it outward, and distort it if it's an extended object. And I'll show you how that works in a second. And so those objects deep in the background that you shouldn't see at all can be revealed. All right? And so that's gravitational lensing relative to something like the sun. Now, the other thing that in the past 20 years or so, we've really gotten good at seeing gravitational lensing by galaxies. And that's thanks to the Hubble Space Telescope. Now, here's an image. Can you cut these front lights, please? Very nice. Okay, so here's an image from the Hubble Space Telescope. Now, see this guy down here? Look at that one. I'm going to enlarge it for you a little bit. Look at it. Look. Look. Good. Look. Not at your computer. Look at this. All right? See that? It's almost a full circle. That's called LRG 3757. That's actually a galaxy. This is the galaxy here. This blue, kind of almost a horseshoe shaped. So if you type in gravitational lensing and then the word horseshoe in Google, this is the one that you'll come up with. All right? And the thing that lenses it, it's not the sun, it's a galaxy right there. So make a note of that. Now you could actually make a sketch of this in your notes. Gravitational lensing. So a lot of times in Hubble space telescope, not a lot of time, a ton of times, Hubble has been able to observe lensing like this, where there's some galaxy way in the deep background, and then there's a big galaxy a little bit closer to us that lenses, and we can actually see behind the galaxy. You know, behind this kind of bright orangey galaxy that's close to us, we can see that. You know, we shouldn't be able to see that blue galaxy. It's kind of smeared out into a horseshoe. Sometimes we just see the galaxy. It doesn't deform very much. Here's a famous one. This is the same galaxy here. This image here and this one here. It's lensed by two different galaxies in this big. Everything in this picture is a galaxy, by the way. It's not stars. It's a galaxy. And we see this all the time. Matter of fact, you can see here's another galaxy. Look at this. This streak here. This one looks like it's lensed a little bit up here. Everything on this image is, so you can see this one's a spiral up here. Everything on that image is a galaxy, not a star. And when they looked at it really carefully, they looked at the spectra. This one and this one are extremely far away. Very, very far away. Billions of light years away. Very faint. So it doesn't smear out like that other one into a horseshoe or an arc. But we can see it. And here's the general layout. Let's take a look at this. This is from the Hubble Space Telescope Science Institute. Basically, the idea is you have some sources back here, you know, way far back away from you. And you're up here in the front. Okay? And the light from those sources, you know, galaxies or, you know, a pulsar or a supernova, it passes by some intermediate galaxies kind of between the source and us. And those intermediate galaxies are a little bit closer to us, and they'll act as lenses. All right? So when the starlight from the galaxy gets to us, here's us observing. So there's three levels here: source, lenses, and observer, us. We actually see that thing behind. It's moved out from behind one of the foreground galaxies. So these ones here, the lenses, those are what we would call the foreground galaxies. They're kind of in the foreground. They're a little bit closer to us than the sources. And these are the faint galaxies over here. And you know, we can see buku stuff this way. It's kind of hard to analyze, but now that we've seen it a lot, it's pretty cool, and it does tell us a lot. And actually, you know what, guys? This is another way of getting the mass of a galaxy. If we can measure the gravitational lensing and get a few basic measurements, we can estimate the mass of an entire galaxy. It's kind of cool. All right, so gravitational lensing we talked about, and trapping photons is the other milieu, the other procedure by which we want to think about gravitational lensing. So deflection of starlight, deflection of galaxy light, and then the event horizon of a black hole. And what we talked about last time towards the end of lecture was, what if you have a spherical set of flash bulbs right at the event horizon of a black hole? All right, and it's represented here as a circular ring of blue flash bulbs. And you set them off for a 1 nanosecond burst of light, red H alpha light. All right, so that's going to be 12 inches thick, and it wants to go outward in this direction. But because it is getting lensed by the curvature of space-time near the black hole, these ones, they try to follow these outward paths. They're aimed in the right direction. And make a side note to yourself. The trapped photons here that we're talking about, these are not streaming past the black hole like the galaxies and the starlight. Those are streaming past the sun. These photons are trying to move outward from the black hole. They're going radially outward, but they don't really get a chance. They never diverge. So they're out here, and instead of diverging the way normal starlight would do, please come sit down here in the front. They're trapped. And so that gives us the best definition of black holes. Adrian, raise your hand. Sit next to Adrian. Okay. Right in the center. Good. So that gives us our definition of a black hole, or of the event horizon, I should say. So you know those photons of light, the 12 inches of light, it doesn't escape and head out into space. It's trapped. And that's equivalent to saying escape velocity is the speed of light, or greater than the speed of light. All right? Now, if you have a set of light bulbs that's further out, like 10 times the distance of the event horizon, 10 times the size of the event horizon, those flash bulbs, the light from those flash bulbs will escape and come to Earth. We'll be able to see it, but they'll still be affected. They'll be redshifted is what it is. All right, so this is kind of where we dropped off last time, that the event horizon is the outermost surface of gravitationally lensed and trapped photons that are trying to escape on a radially outward path from this central object that we call a black hole. Now, I'm going to talk about the distance now from the center of the black hole. So let me give you a little rundown on spherical coordinates. The simplest black hole is one that's spherically symmetric. Right? So the coordinates around a black hole, the best coordinates to use, most of the time anyways, are, like latitude and longitude. Okay, same as on a globe of the Earth. And then the radial distance from the center. Now, we don't do that with globes of the Earth because every human location is pretty much the same distance from the center, 6,371 kilometers. The top of Mount Everest is a few kilometers further from the center, and the depth of the bottom of the Mariana Trench is a few kilometers closer to the center, but pretty much everything's at the center. So, on a globe of the Earth, we just think about latitude and longitude. Okay? And of course, if you're in an airplane, you got to think about latitude, longitude, and altitude. But pretty much, but in a black hole, yeah, the radial distance and the center of the black hole is the key. All right? Now, the customary name for this kind of a black hole, spherically symmetric, it's called the Schwarzschild black hole. And this is one of those German names, kind of like mine, that you can, that's like infinite opportunities to mispronounce and misspell. So if you feel like you're going to blow it, just say, oh, spherically symmetric black hole. Perfect. All right. Now, and a side note, I thought about making number 5 here. There's other black holes, and this is kind of idealized because most of the time a star has some angular momentum. And a spinning black hole that's spherically symmetric but spinning is significantly different. All the event horizons and stuff are changed by the fact that you're spinning. Much more difficult to tackle, but we've got a handle on those. Anyways, let's talk about in and around a black hole. Now, the outermost trapped surface is called the Schwarzschild Radius. That's the event horizon. And the distance to it from the center is the Schwarzschild Radius. Now, according to the theory of relativity, there's a ton of geometry and trig and calculus behind this formula, but basically it boils down to this. 2 times Newton's constant, capital G, times the mass of the black hole. So whatever, so your core collapse, you have like maybe 7.2 solar masses worth of matter crushing and collapsing down to a black hole. That would be that. 7.2 solar masses. And then c squared in the denominator is the speed of light squared. All right. Now, and this just happens to work out to meters. Now, scientists, as a rule, are lazy. Just, slacking. We do a lot of that. And so our shorthand for the Schwarzschild radius is just 2m. Okay? So when I say r equals 2m, I'm talking about the event horizon. If I talk about r equals 3m, I'm talking something a little bit further out. If I talk about r equals 0, that's the center of the black hole, and that's where the trouble really is. The event horizon is troublesome, but the center of the singularity, the center of the black hole is really the difficult part. Okay, the next interesting distance or kind of location is distance 3m. All right, so this is again using the astrophysics shorthand. 3m, that's known as the photon orbit. And if you have a photon of light that's going perfectly sideways, it's not dipping in towards the black hole, it's not dipping away from the black hole. If it's going perfectly sideways at that distance, it'll continue in a perfect circle. Right? So photons of light, it's the perfect place where the curvature of space-time, any photon, infrared, X-ray, you name it, they'll orbit at r equals 2m. The problem with it is it's unstable. So if you're just a little bit slanted inward, you'll stay near that for a little bit of time, but eventually you'll spiral in. If you're slanted a little bit outward, away from the black hole, you'll orbit maybe a few laps at 3m, but eventually you'll ease on out, somewhere, into the stars. Right? So it's kind of unstable, but theoretically, it's a perfectly circular orbit for photons only. Massive objects, they can orbit anywhere they want in a circular manner outside the event horizon. Okay, r equals 0. That's the center of the black hole space-time. And that is a space-time singularity. That is where all the matter that forms the black hole, so for instance, core collapse supernova, all that iron core gets squeezed down into 0 volume. And we don't really understand how and why that's the case. But as we'll see here, we know that it is the case if the theory of relativity is kosher, and we've verified the theory of relativity out the wazoo, so we know it's pretty rock solid. So stuff, even if we don't understand it, we understand that stuff has gone down to r equals 0. That means you've got a finite mass in a 0 volume. Your density, you can't even write the number down for the density. All right. Now, fourth distance that is key. So the first one is the Schwarzschild radius, 2m. Second one is the photon orbit, 3m. Third one is the singularity, r equals 0. And then the fourth one is infinity, the limit r going to infinity. And out that, so that's like relative to Cygnus X1, that black hole there, we're at infinity here. So our space-time is relatively flat. The further you get away from the center of the black hole, the flatter and flatter your graph paper gets. Right? But close in, R equals 3m, you've got curvaceous graph paper in there. Significantly, noticeably curvaceous graph paper. R equals 2m, forget about it. You got bodaciously curvaceous graph paper in there. All right? Now, that's the lay of the land. In terms of the spherical coordinate r, the distance from the center. Now, as I mentioned before, the best way to understand a black hole is to think about its light cones. So now let's look at the light cones as they behave near r equals 2m. And I'm going to give you a diagram here, and this is probably the easiest diagram to draw recently, but it's going to lead to a lot of unusual concepts. So here it is. On the left is, far left is r equals 0. And I'm going to look at just one axis going out from the left side to the right side. So r equals 2m is measured, and you know what it is? It's 100 pixels from the edge of my computer screen. And then 3m is another 50 pixels. And then I want 10m, and I want you to put in 5.5m as well. And what we're going to do is look at the light. We're going to look at a laser beam. Those blue lasers that you can buy, the ones that are really bad. If you shine them, like if you shine them in somebody's eye, they can really hurt your retina. Even the red ones, you shouldn't do it. But the blue ones are really, but they burn right through. You can see them a long way away. They're really powerful. And so we're talking about a blue laser, and we're going to talk about you operating a blue laser at these distances. 2m, that's the event horizon. 3m, that's the photon orbit. And then an intermediate time, I was running the numbers last night, and I thought, all right, let's use 5.5m. There's something special about 5.5m. If you have and actually the numbers and the colors and stuff that I'm going to give you in this slide are for Sagittarius A star, the black hole in the center of our galaxy. All right, so let's say that you're in a spaceship going towards the center of the galaxy, Sagittarius A star, which we talked about in the first week of class, and you're in a mothership, and you're going to dive out of it when it gets to 10m. And you're going to send signals back to the mothership and back to Earth with your blue laser. So you're going to do dots and dashes. You're going to do Morse code, SOS, or whatever you want to send. All right? And then here's over here, I put a globe of the Earth and R going to infinity. And there's a little squiggle here to mean that that's where the scale or the axis breaks, and we take a chunk of the axis way out where Earth is. Okay, so there's a little break there, right where that squiggle is. All right. So inside 2m, there's a circle there. That is the black hole. All right. 2m is the event horizon. 3m, I have a circle, kind of a greenish circle. That's the photon orbit. So the Roy G. Biv, I put a green Roy G. Biv photon there. That's its orbit, theoretically. And we're going to talk about some of these other distances, 5.5 and 10m. All right, now, here's us. Here's our home planet. And let's say that, you know, the blue laser that you're using was built on Earth, all right? And when you jump out of the spaceship at 10 m, so let's say that the spaceship is hovering at 10 m, okay? It's not going in, it's not going out, it's just got it's firing its rockets, it can hover there for a minute. And you're out on the side of the spaceship, and you take the blue laser beam and you shine it into your hand, and you say to yourself, oh yeah, this is blue, okay? So for you, the laser beam is going to look blue. It all looks normal. And you're wearing a wristwatch, and you know, your Timex is going 60 seconds per minute, no problem, all right? But now when you shine that blue laser towards the Earth, so you're hanging on the spaceship now, 10 m, and you shine, you bleep out, okay, in Morse code, towards the Earth. They'll get it, you know, depending on how far away they are, but it will be blue, it'll be red shifted into the greens. It won't be red. It starts out blue, but by the time it gets to Earth, they'll be perceiving it as a green photon. And I wrote down the color. Okay, so go ahead and write down a few notes here. The blue laser beam that you can buy in the store is 532 nanometer wavelength. All right, so make a note of that. So this blue laser, made on Earth, wavelength 532 nanometers. Yeah, the blue laser, the wavelength of it is 532 nanometers. You got that? In the back? In the very back? Yeah. I could hear you asking a question over there. Okay, so yeah, you get it out of the box, 532. It probably even says it on the box. I mean, I looked it up on the internet last night. So, all right. But by the time you shine it, it's coming out of a black hole, and one of the effects is gravitational lensing. And the other thing that happens with photons is they get redshifted or blue shifted, and this is a redshift. It's heading out towards Earth. So by the time it gets to Earth, the people on Earth, they're not going to measure 532. You know, they're going to put it through diffraction grating, and it's going to swing out into the green area, 594. So make a note of that, 594.8 nanometers. And and make a note, that's from 10 m to infinity, to Earth. So if you shine that blue laser from 10 m, safe distance, close but a safe distance, out to Earth, by the time it gets to Earth, it'll be green. Okay, that's not too bad. And you know, the amount of information that you can squeeze into a fiber optic depends on the frequency of the laser. You ever hear that word bandwidth? You know, you got a high bandwidth. It means you got a high frequency. Your signal's a high frequency signal, and you can blaze a lot of megabytes in there. So once you start redshifting into the green here, into the G, you're losing information capacity. All right, so less information you can send. All right, now let's get a little closer. 5.5. So now, here you are, you've jumped off your mothership, and you're drifting down. And you know, the average density of the inside the event horizon of the black hole Sagittarius A star is not that bad. So you might still be okay at 5.5 m. All right. So you're at 5.5 m. You're just kind of sliding through there, heading towards the black hole, and you shine it into your hand, and yeah, blue. It's still blue. So for you, it's blue. You're an observer. In your frame of reference, it looks blue. By the time it gets to the mothership at 10 m, guess what color it is? Good old H alpha. From 5.5 m out to 10 m, my 532 nanometer blue laser is going to shift all the way into the reds, and it's going to be 660 nanometers. That's pretty darn close to H alpha. All right, I ran the numbers last night. Okay, that's what you get. So when you're down there at 5.5, yep, it looks blue to you, but the mothership is going to read it at 660. So you're going to be blazing out those SOSs, and the density of information that they're getting is already down in the red. All right, so you're losing bandwidth. And by the time, and so you do a copy CC to the planet Earth. By the time it gets out there, it's a little bit redder. Go ahead and make a note. 667 nanometers at infinity. All right, so you're at 5.5 M, and it looks perfectly, and your wristwatch is just clicking along. And you've taken a finite amount of seconds to get from 10 M down to 5.5, and you're going to take a finite number of seconds to get into the event horizon and then through it, and you'll go through the event horizon. All right? But your outgoing signals are redshifted. And so, from 5.5, the 532 nanometer blue laser is redshifted to 660 at the mothership, and 667, another 7 nanometers by the time it gets to Earth. So most of the redshifting is down close to the black hole. All right? And etc. So every inch closer, your blue, and I calculated about 2.02 M, really close to the event horizon. You're down in the microwaves. You're at the same temperature as body temperature. So the blue laser, by the time it gets out to the mothership, it's going to be way in the infrared, and you're just not going to be able to beam out much information. You'll be beaming it out, but they're not going to be getting much information. They're really low bandwidth. All right. So you dive in from 10 M with your wristwatch, and to you it still looks blue, and your wristwatch looks fine. But for people on Earth, people at the mothership, things look a lot different. Your signal is redshifted. It's redshifted at the mothership at 10 M, and it's redshifted all the way back at Earth at R equals infinity. Now, let's go through some common misconceptions. A lot of times you read about this on the internet. An astronaut dives into a black hole and they turn it to spaghetti. That's one of the tidal effects. And that's righteous. But another thing that you sometimes see on the internet, the astronaut's clock runs slower. No, that is incorrect. Oh, we got to go through all these again. Sorry. I'm starting to get cranky here with all these misconceptions about relativity. Okay? Time doesn't run slowly. Your Timex is clicking just, if your resting heartbeat is 60, then that means your Timex, your heartbeat's going to be going at 60 beats a minute, and the Timex is going 1 tick per second, and that doesn't change. But what does change is this. Observers disagree about time measurements. All right, so make a note of that. Your wristwatch, to you, you're in motion with the clock, so it looks hunky-dory. But now, observers on Earth, our clocks are going to go to infinity before we see the last tick on the astronaut's Timex before he goes into the black hole, right? And the black hole, the astronaut, he'll tick off, like 37 seconds or 2.5 days if it's a really big black hole. You know, so depending on where he jumps out, you know, take a finite amount of his time on his Timex. But for the clocks back on Earth, and remember, you know, if you think about dots and dashes coming out, information capacity changing, you know, with the redshift, you're not going to get, if he were to pulse out a blaze of blue laser light for every heartbeat, they'd be getting them in infrared by the time he gets close to the event horizon, and they'd be, they'd come in over the course of days, months, and years. All right? The clocks would disagree. And theoretically, from Earth, we would never actually see him cross the event horizon. He'd know that he's in the event horizon. He'll cross in, 37 ticks of his Timex or something. But we won't. Our clocks will go to infinity before anybody sees it. Matter of fact, they won't see it. All right? Nobody will see it when it's going into. And that's the essence of relativity. The measurements, the distance measurements, and the time measurements disagree depending on the state of motion of the observer. Let me repeat that. The time measurements and the distance measurements disagree depending on the state of motion of the relative state of motion of the two observers, or the relative curvature in which the two observers find themselves. And that's what we got here. We got a deep curvature nearing the event horizon and flat, zero curvature by Earth. So those two observers are going to disagree about distances and times. And that's what you should say, not that the clocks slow down. They appear to slow down for us, but our clock is going at 60 beats per minute. His is going at 60 beats per minute. But when you try to communicate from one reference frame to the other, then you get disagreements. Another thing, curvature means that the outgoing photons are redshifted. And from Earth, here's the other thing. If you're looking at his wristwatch, okay, and you're looking at his laser signals, they get redder and redder. You know, and he doesn't have to get very close before that blue is shifted to H alpha. And a little bit closer than 5.5 M, he's going to be in infrared. He's almost there now. 660, a little bit closer, he'll be infrared. He'll be in the 700s. And I worked all that out. All right? And then he'll go into microwave. And then into FM radio. And then into AM radio. And then then ultra low frequency, just infinity. And so the frequency gets really small, the wavelengths gets really big. So your information capacity is diminished. All right. Now, last couple slides here. Here's my diagram again. Now let's take a look at the light cones. This is why we're doing it. When you're out here far from the horizon, the event horizon, everything looks hunky-dory. The light cones are 45s. No problems. But now, in addition to redshifting, that's what happens to photons. What happens to light cones is they get tighter. So everything's okay out there towards infinity, where space-time is flat. But like 10M, yeah, you got some serious tightening up. The light cone is no longer 45 and 45. All right? You got a lot of tightening up on that end. So now, when you cross, let me go back and do that. Here's 45. Everything's copacetic. Here's 10M, starting to tighten up. Now watch what happens when you cross the event horizon. I'm going to blaze this one with fire. See that? The light cone tips over. It doesn't tighten up. It tips over and it gets wider. What? What the heck? Yep, that's what happens. So inside the event horizon, you're still thinking light cones. Light cones still exist. You can still draw them. They're just tipped over. They're rotated 90 degrees. Now let's think about what that means. Here's a close-up. At 2m, your light cone is tipped over and it's wider. Okay? Now the time axis relative to the light cone is always right down the middle of the light cone. So here's the time axis. Bing! Right there. So go ahead and write down 2m, your light cone tilting in, and there's the time axis. And guess what? Your time axis is pointed right at r equals 0. And that is why we say that r equals 0 is the future of everything inside the event horizon, because the light cones have tipped over. The time axis for this observer, he's crossed the event horizon, and now if he were to sit down and write, okay, my light cone is, whoa, my light cone's tipped over. You know, it's pointing right at r equals 0. That's the inevitable point in his future, r equals 0. So that means, and that's another way of saying that everything gets squished down to 0. R equals 0 is the future of everything, you know, whether it's a short time or a long time. Now, what does it mean? The omnifuture, the future of everything inside the event horizon is r equals 0. What does that mean? Well, think about a regular calendar. Go ahead and make a little sketch of a calendar. And here's what we know about regular calendars. You know, you go, 1 minute every 60 seconds. That's the normal, speed that we move across time. And 1 day every 24 hours. And we have those little blocks, and you go through the calendar, and So, but you only go in one direction through the calendar, always forward. And so one way of saying that is that a specific time, like next Tuesday, is inevitable. The inevitable point, the inevitability, is a day in the future, like Tuesday next week. That's inevitable. We're coming at it 60 minutes every hour. But the other 3 dimensions, we walk. We walk those as we please. We go up the aisle. We're going in 3 dimensions. You get in a plane, you travel in all 3 dimensions, no problem. Now, inside the event horizon, a little bit different. The inevitable point is a spatial point. The center, r equals 0. The walkable dimensions now include time. And so for that reason, one way that you could talk about that tipped over light cone is that now the calendar of days has become a chessboard that we can walk across. We can't do it out here in flat space-time, but inside the black hole, my wonderful students, thinking about the future and the past, it's a lot to think about. But this change of the roles of space and time occurs exactly at the event horizon, the outermost surface of trapped photons. So make your future a good one, as the saying goes. And that, my wonderful students, is all I have to say about black holes. Now, we have a mega review coming this weekend in web courses. And what I want to do now is a mega review in class. And what we're going to do, Adrian, could you come up here and help, please? I'm going to hand out these review sheets to keep your clickers on. Just hand these out in bunches. Don't count them out. Hand these out in bunches. Could you come up and help hand out? Just do the middle group here. All right, take some and just hand them out in bunches, a few to each row. And if you have, do this side over here. Go ahead, but do this side over here. And just hand them out quickly in rows. And start. You can start with the questions. If you have extras, send them backwards to the back of the room. All right, very good. Just hand them out in bunches. And I want to have the leftovers too, if you please.